2's complement is the way a computer stores both positive and negative whole numbers using only zeros and ones. Imagine a row of light switches, each representing a binary digit bit. The most left-hand switch is the sign switch. If it is off 0, the number is positive. If it is on 1, the number is negative. For an n-bit word, the value is calculated as value equals -2 to the power of n-1 times b of n-1 plus the sum from I equals 0 to n-2 of 2 to the I times b of I, where b of I is the ith bit, 0 or 1. To get the negative of a number, you flip every bit, like turning every light switch and then add 1, just like counting up one more step after all the lights are turned on. Example with 8 bits, plus 5 equals 0000 space 0101. Flip bits becomes 1111 space 1010, add 1 becomes 1111 space 1011, which the computer reads as -5. This system lets the same hardware, the ALU, add positive and negative numbers without any extra tricks. When a programmer writes an instruction such as add R1 #-5, the #-5 is called an immediate operand because the value is written directly inside the instruction itself, not taken from memory. The processor's instruction format has only a limited number of bits to hold that number, often fewer than the full width of a register. If the immediate field is, say, 5 bits, the value -5 is first encoded in 2's complement using those 5 bits, 1011. When the CPU fetches the instruction, its sign extends the 5-bit pattern to the full register size. Because the most significant bit, the sign bit, is 1, the CPU copies ones into the higher bits, turning 00000000001011 into 111111111111. This keeps the numeric value as -5 even after it lives in a 16-bit register. Sign extension is like stretching a rubber band that already has a minus sign at its left end. You pull it out while preserving the sign. The flag register is a small set of single-bit indicators that tell the program what happened during the last arithmetic or logical operation. Think of them as traffic lights at a tiny intersection inside the CPU. 0Z flag turns green 1 when the result of the operation is exactly 0. It is like a sensor that says all the cookies have been eaten. Carry C flag becomes 1 when an addition generates a carry out of the most significant bit or when a subtraction needs a borrow. Imagine adding 2 piles of blocks. If the top pile overflows onto a new shelf, the carry flag lights up. Sign S flag copies the most significant bit of the result, indicating whether the result is +0 or -1 in 2's complement. It is the same as looking at the leftmost light switch. Overflow V flag signals that the signed arithmetic overflowed, meaning the true mathematical result was too big or too small for the available bits even though the carry flag might be 0. For example, 127 plus 1, binary 0111111 plus 000000001 produces 100000000, which looks like -128. The V flag tells you the signed addition went out of range. Programs test these flags with conditional branch instructions to decide what to do next. Most simple microcontrollers have a single-cycle multiply or divide instruction, but the hardware actually performs a short sequence of steps behind the scenes. For an 8-bit times 8-bit multiply, the CPU generates 8 partial products. Each bit of the multiplier either adds the multiplicand shifted left or adds 0. These partial products are added together in a ripple carry adder, and the final 16-bit product is placed in a pair of registers, often called HI and LO. The instruction might look like MULR0, R1, where R0 holds the low byte, and R1 holds the high byte after execution. Division works the opposite way. The CPU repeatedly shifts the dividend left, subtracts the divisor, and sets a bit in the quotient register if the subtraction succeeded. This is similar to how you long divide on paper. The sequence finishes when all bits of the dividend have been processed, leaving the quotient in one register and the remainder in another. Bitwise logical operations treat each bit of a word as an independent tiny switch. The 4 basic operations are AND pronounced, and a bit is 1 only if both corresponding bits are 1, like a gate that only opens when both keys are turned. OR pronounced, or a bit is 1 if at least one of the bits is 1, like a light that shines if any bulb is on. XOR pronounced exclusive, or a bit is one if the bits are different, like a toggle that flips when exactly one switch is up. Not pronounced not flips every bit, like turning every switch to the opposite position. Masks are constants built with these operations to isolate or modify selected bits. For example, to keep only the upper byte of a 16-bit value, you can AND with 0xFF00, binary 1111111000000000. To set bits 0 to 3 to a particular pattern, you can OR with 0x000F. Masks are like stencils that let you paint only certain parts of a picture. Shift instructions move all bits left or right by a fixed count. A logical left shift SHL inserts zeros on the right and discards bits that fall off the left. Mathematically, it multiplies an unsigned number by 2 to the n, where n is the shift count. A logical right shift SHR inserts zeros on the left, dividing an unsigned number by 2 to the n and discarding the remainder. An arithmetic right shift SAR keeps the signed bit, the leftmost bit, unchanged while shifting, so a negative number stays negative. It's like dividing a signed integer by 2 while rounding toward negative infinity. Rotate instructions ROL and ROR move bits around the ends instead of discarding them. Bits shifted out on one side re-enter on the opposite side. Rotates are useful for cyclic buffers, checksum algorithms, or for generating pseudo-random numbers. Think of a carousel where writers' bits that step off the right side immediately hop on the left side. When a calculation produces a result that is larger than the biggest positive number a register can hold or smaller than the most negative, the CPU can either wrap around normal overflow or saturate. Saturation means the result is clamped to the nearest representable limit. For an 8-bit signed value, the limits are -128 and +127. If an addition tries to produce +200, a saturated result becomes +127. Detecting overflow is done with the overflow flag for signed operations, or the carry flag for unsigned ones. A common software technique is add R0, R1, R0 equals R0 plus R1. BCC no_carry, branch if C equals 0, no unsigned overflow. For saturation, you may use a conditional move after checking the flag. BVS saturate, branch if signed overflow V equals 1. Normal paths. Saturate label. Move R0, hash max, load saturated value. Some processors even have a single instruction like add.sat that does the check and saturation internally. Memory mapped I/O treats certain addresses in the processor's address space as doors to external hardware, instead of as locations in RAM. Reading from or writing to those addresses automatically triggers the peripheral hardware, for example a LED register, a UART data register. Load register 0 with the constant address hexadecimal 0x4000_10, which is the address of the LED port. Move immediate value hexadecimal XFF into register 1 to turn on all LEDs. Store the value from register 1 to the memory location pointed to by register 0, writing to the LED port. Because the address is just another value, you can combine it with arithmetic or logical operations. For instance, you can mask the status register of a button panel, shift the bits to align them, and then add a constant offset to point to a different control register, all without leaving the CPU's instruction pipeline. This tight coupling lets programs react to hardware events in a few clock cycles, making embedded systems fast and efficient.